Welcome to session 9 on Arista TAC webinar series 2024-2025. First of all, I would like to introduce myself. My name is Vignesh Jyotinarayanan, and I'm a technical lead here at Arista TAC team. So we are on a short break, and now we are back with part 3 on troubleshooting a networking fabric. We'd like to take this opportunity to connect with our customers and to share our knowledge and troubleshooting insights for the experience gained through the TAC environment over the past years. So the technical presentation for today will be done by Madhukar Sharma. Madhukar is one of our senior technical solutions engineer here at Arista TAC. I would like to highlight that there is a Q&A option in the TAC webinar where you can post your questions, and one of the Arista experts will be able to answer the questions. And also for the customers who have registered for this webinar before February 24th, you would have received an email from us with the troubleshooting topology link. For the customers who have registered after February 24th, no worries. We're going to put this link in the chat for your reference. Next slide, please. In the Q1 of 2024, we did 3 webinar sessions on troubleshooting network issues related to latency, black holing, and packet drops. Later in the Q2 of 2024, we did a 3-part webinar sessions on multicast related troubleshooting. In the Q3 and Q4 of 24, we did 2 sessions on troubleshooting A networking fabrics. And now we are in the Q1 of 2025 doing the 3rd and the final part on troubleshooting A networking fabric webinar. So all these sessions and its recording and its content is available in the Arista Community Central article link attached to this slide. And also, I would like to highlight that we are now offering customized troubleshooting training for our customers. And these trainings are tailored for platforms and features specific to the customer network. And also, we'll be providing key recommendations from Arista experts to improve the efficiency and performance of your fabric and to avoid any outages. For more information on these sessions, please reach out to tac-custom-training@arista.com, or you can discuss with your Arista accounts team for more information. Next slide, please. Before we get started with the troubleshooting scenario for today, let's talk a bit about what it takes to build a superior A networking fabric. First of all, it needs to be a lossless network. It should support high bandwidth speeds like 400G, 800G connectivity. It should be low latency forwarding capable. Advanced load balancing features like dynamic load balancing, etc., should be supported on those fabric. And ECN, PFC congestion management features should be available. And smart tools like Arista CloudVision telemetry, Arista latency analyzer for monitoring and visibility to detect any issues before and fix it before they're creating any impact. And also the fabric should be able to interconnect hundreds and thousands of GPUs together, providing superior performance. Arista's A networking platforms and features are purpose-built for satisfying all these requirements. And also Arista provides a range of fixed modular distributed platforms for small, medium, and large-scale A clusters. In order to know more information about Arista's A networking platforms and solutions, please check our complete portfolio at Arista's A Networking Center link attached to this slide. Next slide, please. In today's session, Madhukar will be walking us through on troubleshooting intermittent traffic drops in the A networking fabric. And he will also be guiding us on how to detect these issues and make the changes to avoid these issues in the future. With this, I'm going to hand it over to Madhukar for presenting the scenario. Madhukar, take it away.
Thank you, Vignesh. Good morning, everyone. My name is Madhukar Sharma, and I'll be your speaker for today's webinar. Now, before we get started with discussing some of the prerequisites in the problem description, let's take a quick look into the topology diagram that we'll be making use of today. So we're making use of a spine and leaf topology, wherein all our devices are 7060px5 devices, and they're running a EOS code version 4.32.1f. And all these devices, the networking devices in particular, are streaming onto CloudVision. Now we have 4 set of leaf devices: the AI Leaf 1, Leaf 2, Leaf 3, and Leaf 4. And each leaf devices have a GPU rack connected to it. The inter-rack communication is possible via a two-way ECMP link, that is via AI Spine 1 and AI Spine 2. And for simplicity, we are using IPv4 addresses on the GPU. And one thing new is that we are using IPv6 LLA between the spine and the leaf devices, but that's only for establishing routing. Now, something which has been a standard across the previous webinars as well, we are using AI flows, which are a Rocky version 2, and they are mapped to traffic class 3. And to provide congestion management on the traffic class 3, we are using ECN and PFC. And lastly, we have LAN-Z enabled on all the leaf and spine devices. And we also have queue streaming enabled on the leaf and spines. So we have all our LAN-Z data streaming onto CloudVision. Now, next, I'd like to take your time to discuss the use of BGP LLA in the AI networks. And something we already know, but IPv6 router advertisement packets play a critical role in ensuring that the IPv6 addresses are configured correctly on the router devices or the multi-layer switches before the BGP session can be established. Now, using IPv6 LLA makes the communication between the peers in the same segment possible without the need of any explicit global IP configuration. And BGP LLA is really useful in networks with high ECMP links, as it uses the link local addresses for BGP peership without the need of configuring any IP explicitly. This allows the router to communicate directly over the same network segment using their link local addresses. With that, let's take a quick look into the problem description for today's webinar. Now, these slides must have been shared with you earlier, but if you don't have the topology diagram or the problem description slide with you, they'll be available on chat. And if you have any questions throughout the webinar, please feel free to post them on the Q&A. Our panelist will be answering to them with the best of abilities. Now, the customer reported a blip in their AI network, which got auto-resolved. And along with that, they had also gotten some alerts for the packet drops in their network. And now they want us to perform a root cause analysis of this event. Now, since we are performing a root cause analysis, we need to first clearly define the problem statement. And that's something we already have. But along with that, we also need a problem, the symptoms being observed by the customer, the timeline of the issue, and a well-defined topology diagram. Now, we are having a topology diagram in place, wherein it's the same that we discussed earlier. And when we checked upon the symptoms observed by the customer, they mentioned that they were seeing some failing AI workloads and inferior performance in their network. When asked about the issue timeline, the customer reported that they had observed this on the February 14th between 4:30 p.m. to 5 p.m. Pacific time. So now, to troubleshoot this, and we need to establish an approach. And since upon discussing the key pointers, we don't have any specific flows that we can look at, or if there is any correlation to the symptoms, we're going to leverage the CloudVision's telemetry services to look at the network events that took place during the time of the issue. So for that, I have a pre-recorded session from the customer's CloudVision setup. So please follow along. And if you have any questions, feel free to post it in the chat or the Q&A. Now, since we are going to use the custom dashboard, which is built on CloudVision, and this custom dashboard covers all the key events which are important to check in any AI network. Now, for this troubleshooting, I have also adjusted the timeline of this dashboard in a way that it covers the issue timeline, which was mentioned by the customer. And we are filtering out the AI leaf and spines by using the container filter, as you can see on the screen and the tags section. Now, these container level filters are basically being used as in, we have put all the leaf and spine devices in a part of same container. In this scenario, that's AI networking webinar, and we're filtering out for the devices using the container filter in this scenario. Now, as we can see here, we see a bunch of green tiles. Now, these green tiles are basically network events for the respective devices in a given time frame. And depending upon the color scheme of these tiles, we'll know what type of event is taking place at a given device at a particular time. So, for example, if it's all green, that means that we have no events that it's taking place on any of the leaf and spine devices during the time of the issue. And depending upon the color coding of these events, for example, if the color of a tile is red, that means that erroneous event took place at a given device or a given time frame during the time of the issue. Now, with that, let's quickly take a look at the various events and see what has happened during the time of the issue. The first one being the device config event. We see that it's all green. That means there was no config changes which were reported on any of the leaf or spine devices during the time of the issue. Now, further looking at the hardware capacity, we see that this is also all green. That means none of the devices were reaching an upper limit to its hardware capacity during the time of the issue, and things looks under control. Now, further looking for the BGP neighbor events, which is basically going to show us if there is any BGP flap that happened during the time of the issue. And when we check this event, we see that there were some BGP neighborship flap events that took place on the leaf devices. Now, this makes us question, why did these flaps happen? And since these flaps are happening all at the same time, could this be related to the issue that we are observing? Now, we'll get back to this in some time, but for now, let's take a look at the events that took place under this BGP event. And we're going to take AI Leaf 1 as a sample device to check for the BGP events that took place. As we can see here, we observed a BGP notification message, which was sent or received, and it's been received or sent for a IPv6 peer. And that's been learned over ET26/1. If we check for the other events under the same sub events, and we see that these are also BGP notification message for an IPv6 peer, and all these notification messages are being sent for IPv6 peers that are being learned over ET26/1. Now, if we compare it to the original topology diagram, we see that we don't have any connections or any relevant uplinks from ET26/1 or any BGP connections apart from these AI spine 1 and spine 2 from the AI leaf perspective. But to investigate it further, let's take a look at the BGP table on CloudVision and see what all BGP peerships were being formed on the AI leaf 1 during the time of the issue. Now, since we had looked at the AI Leaf 1 for the sample events, we're going to continue looking at BGP event or BGP peerships for the AI Leaf 1 and confirm what was happening during the time of the issue. Now, as we can see here, during the time of the issue, the AI Leaf 1 was forming 5 BGP peerships. And let's take a look at what these peerships are. So if we check the first peer IP that is ending in with C0E9 and we compare it to the topology that's on the screen, we see that that peer IP is present on AI spine 1. And that peership being formed is with the AI spine 1 from the AI leaf 1's perspective. If we look at the other peer IPs and the second one, which is ending in with E129, we see that this is the IP which is present on AI spine 2, and this BGP peership is being formed between AI leaf 1 and AI spine 2. Now, as discussed earlier, these are the two neighborships which are expected as per design and are providing a two-way ECMP link for the inter-rack communication. But if we look at this BGP table or the peership table, we see 3 other IPs, one ending in with CB41, the other one ending in with D585, and the last one ending in with A75. Now we see that there are these 3 other neighbors that came up around the time of the issue, but we are still not aware of who owns these IPs and how did we learn about these IPs on the AI leaf one. So for that, we're going to make use of the neighbor discovery table, and we're going to check the neighbor discovery table on the AI leaf one and see how did we learn about these IPs. And we're going to make use of the endpoint search to check who owns these IPs. Now, if we see this diagram, this table, we see that these IPs that we were talking about, these are being learned behind ET26/1. Okay, so that's one data point, and let's put that in our pocket for now. And we're going to make use of endpoint search to confirm and see which device owns this IP. And for this one, we're going to take a sample IP which is ending in with CB41. And let's use endpoint search to figure out where this IP is hosted. Now the endpoint search directed us to AI leaf 3, which means that this IP was hosted on the AI leaf 3 device. Now, if we look at the topology diagram again, we can see that the AI leaf 1 and leaf 3 have no direct connections. So how did we learn about this? And that's something we know that we learned this behind ET26/1. And we need to figure out what is connected to this ET26/1 by which we are learning this IP. But before we do that, let's take a look at the endpoint search and perform this operation for the other 2 IPs that we saw being formed as a BGP peer on AI leaf 1. Now, upon performing an endpoint search for the other 2 IPs, we see that the IP ending in with D585 is hosted on AI leaf 4, and the one ending in with A75, that's hosted on leaf 2. Now, these are all AI leaf devices, and these IPs are hosted on them. And since there are no direct connections between the leaves in general, we need to figure out what's connected to this ET26/1, since we can only learn about these IPs if they're a part of the same segment. So we're going to check for the details on ET26/1, and let's click on that. And let's check the interface details and for the LLDP neighbors. As we can see here, we see that the ET26/1 on the AI leaf 1 is connecting to a device called localhost. Okay. Now this device is something we don't have any context on and was not part of our original topology diagram. So, let's check with the customer if they have any insights about this particular device, or, what is this device and how is it connected to the ET26/1 on the AI leaf 1. Now, upon checking on this with the customer confirmed that this is a device which is supposed to be a new spine device. And since it's not having any host name, that's why we see the name localhost.aristanetworks.com. And this is supposed to be provisioned, but it's not onboarded as yet. But seems like someone had cabled this device and connected the link between the new device and the leaf without shutting down the uplinks or moving them into a no switch port mode. And hence, this local host device ended up acting as a layer 2 bridge between all the leaf and the spine device. And since we saw that the BGP configs on the leaf devices were completed, as in we had activated BGP neighborship formation capabilities on ET26/1, we were able to see these leaf-to-leaf BGP neighborships getting formed. The customer also confirmed that at a later time, the links were, shut down. And that probably explains why did we see those BGP flaps during the time of the issue. Okay. So now that we have established that what led to these BGP neighborship formation on the leaf devices, and why did we see these neighborship flaps, but we still need to understand why is this causing an impact to the AI workloads. And for that, we're going to take a look at the routing table on the leaf devices and see if there were any changes reported in the routing table during the time of the issue. So for that, we're going to again, make use of CloudVision. So let's move on to the CloudVision screen. Now, as we can see here, we have a bunch of IPs or prefixes. Now, these prefixes are specific to the GPU interact communication. And if we see these, routing, we see that earlier, the next hop value for the individual prefixes, such as 10.2.2.0/24, 10.2.5.0/24, and 10.2.7.0/24 on the AI leaf one were being learned or being routed over ET7/1 and 9/1. Now these are the two-way ECMP links that was via AI Spine 1 and AI Spine 2, and we should have been routing those as per original design. But during the time of the issue, we see that the ET26/1 that is being more preferred, and that is the link which is connecting to this new spine device. Let's take a look at the other prefixes, and we see that a similar result is being observed for the other prefixes in the routing table as well. And let's quickly confirm the result on the AI leaf 2 as well. As we can see here as well, for the prefixes, which are again, these prefixes, if we compare it to the topology diagram, these are the prefixes being used for the inter-rack communication. And we have some sample GPU IPs that are mentioned in the topology. These prefixes were originally supposed to be learned via ET11/1 and 9/1, which were again the two-way ECMP links via AI Spine 1 and AI Spine 2. But during the time of the issue, the ET25/1, which was the link connecting to the new spine or the local host, that was more preferred. Now, as per design, the customer mentioned that these are IBGP neighborships, and they were using a non-default local preference value on the the neighborship between AI leaf 1 and spine. But seems like since the the BGP neighborships that were formed between the leaves, they were using or falling back to a default local preference value, which was higher. It was preferring this path over ET25/1 or the link on towards the local host as a more preferred path during the time of the issue. Let's quickly take a look for the the other prefixes on the leaf 3 and see if those were also being impacted during the time of the issue. As we can see here for the leaf 3 and the leaf 4 as well, we are seeing the routing to be changed. The more preferred path in all these scenarios seems to be the one which is by a local host, and that's something which is due to the local preference or the preference value. As we can see on the screen, the preference value was set to 2200 for this neighborship between the leaf devices, and those are the ones which are getting more preferred as a path in the issue state. Now, we do understand that there was a new path that was formed during the time of the issue, but we still need to understand on how did it impact or degraded the the performance in their network. Since any change in routing or the triggered in the suboptimal routing that we see here should have caused a blip, and that is something that the customer also observed. But when the routing had changed, the flow got rehashed, we shouldn't have been seeing any performance issues. But since the customer had also mentioned about some packet drop events that took place on the network, let's take a look at them at the dashboard that we looked at earlier and see if there were any packet drops which were reported on any of the leaf or spine devices. So for that, we are again going to move on to the same custom dashboard that's built on CloudVision. And we're going to check for the other events that took place on the leaf and spine devices. Now, checking for the events for the interface flaps in particular, we see that it is all green. So that means the link stability has been there on between all the leaf and spine devices, and we didn't see any interface flap happening on any of the leaf and spine device. Further checking for the interface errors, we see that the interface errors on the leaf and spines were also not there during the time of the issue. But when we move on to the pause frame event, we see a pause frame event taking place on the AI leaf 3 device. Now we see here that there were two events wherein we had transmitted pause frames over 24/1, which is the link connecting to the local host. And we also saw a pause frame event for received pause frames over the 21/1. Now that probably might be a case wherein the traffic was flowing through the high speed to a lower speed link on the GPU, which triggered sending of pause frames from the GPU perspective. But let's not focus on that at the moment. But the pause frame that we are sending on the AI leaf 3 is one data point that supposed to be noted. And let's take a further look on the other events that took place around the same time as well. Now, if we see the interface discard events, we see around the same time that we saw some pause frames, we are also seeing some in discards on ET24/1. And again, those are being observed for AI leaf 3. So that means that, although we were sending out the pause frames towards the local host, we were still seeing some in discards to happen. And, checking for the other events, we don't see any ECN marked events, but let's take a look at the LANZ. And if we look at the timeline of this event as well, this coincides with what we saw on the in discards and the pause frame as well. So that means that we were seeing congestion happening on the AI leaf 3. And that's when we were observing these packet drops and pause frames to be sent. Now, this is not new since the customer had mentioned alerts for packet drops, but we need to confirm if this was impacting any of our AI workloads, or what traffic class was this, the pause frames were being observed for, and for what traffic class were we seeing the congestion to happen as well. And that will help us explain why these packet drops were being observed. And for that, let's take a look at the CLI session on the AI leaf 3. And we are going to check for the LANZ output. Well, one context or just a heads up, this recording is from 15th of Feb. So any output that you see is going to be correlated to a timeline which is in accordance to 15th Feb. So coming back to the LANZ output, we're going to make use of the show queue monitor length output in this case. And to limit the number of samples on the screen, we're going to use the limit 15 samples keyword. And upon seeing this output, we see that there is no active congestion going on, but the last congestion event that took place on AI leaf 3, and the timeline of this recording, as I mentioned, was 15 Feb. So, the timeline of this congestion is on 14th of Feb, which is again the date when the customer had observed this issue. Now, if we check for the traffic class for which we had observed this congestion to happen, we see that the congestion was happening for traffic class 3 on the AI leaf 3. Now, further again, checking for discards, and since we had seen a packet drop event in the customer monitoring tool as well, and even as a part of the CloudVision event, we are going to run the show interface counter discards output. And we see that we were seeing in discards in the ET24/1 interface on the AI leaf 3. Okay. Now, let's also check for the priority flow control counters. And we're going to see what traffic class were we sending and receiving these pause frames for. As we can see here, the ET21/1, that was the one which is connecting to the GPU rack. That's one where we were receiving some pause frames for traffic class 3. And that's again something which was due to the change of traffic from a high speed to a low speed. But if you look at the ET24/1, which was the uplink towards the new spine or the local host, we were sending out pause frames towards the local host device for the traffic class 3 as well, to manage the congestion which was being observed in traffic class 3. Okay, so these are all the data points that we collected from as a part of our root cause analysis. Now, to stitch it together and perform or conclude on our root cause analysis, let's go back to our slide deck and confirm on the other details. Now, as we saw that there was a new spine which was cabled and the connections were made to it from the leaf devices, but the port config on the local host side was not appropriate. We didn't shut down the uplinks, or nor did we changed it to no switch port mode, and that made the local host device act as a layer 2 bridge and forwarded across the IPv6 packets across the leaf device. Now, since the router advertisement packets were being exchanged between the leaf devices, we saw the BGP neighborships to be formed between the leaf devices as a result of the BGP LLA. And since these new neighborships were formed, this induced changes in the inter-rack communication, and we saw that the two-way ECMP path by the spine was no longer the preferred one as a part of the inter-rack communication, and we were preferring the path via the local host as a more preferred path to send traffic from one rack to the other. Now, we also observed some packet drops or the in-discard events on the AI leaf 3, and PFC did get activated to manage the oversubscription or congestion that was happening on the AI leaf 3. However, since the new spine was not configured with PFC, or it could not manage the oversubscription, and we saw oversubscription in the entire network, and that caused the AI jobs to be failing due to the inferior performance. Now, what can be done to avoid such situations? One of them is using CloudVision, as CloudVision has its provisioning services as well, and you can avoid any sort of misconfig and review the config changes real time before actually executing any change control. And the other thing is that when we are provisioning new links between the spine, or adding more ECMP links, we definitely need to make sure that we put the uplinks in a L3 mode, which is no switch port mode, or we put them in a shutdown state before it is configured with the entire appropriate config. And with that, that's the summary for our today's webinar. And I'd like to call Vignesh back for the concluding words.
Thanks, Madhukar, for the detailed and the structured presentation on troubleshooting the intermittent packet drops in the AI networking fabric. So we have also added a link in the chat for providing your valuable feedback on these sessions. And also the contents related to this webinar, the recording, the slides, the Q&A will be made available to the Arista Community Central page shortly. And also we will be keeping the session open for a few more minutes for answering any questions in the Q&A section. And with this, we are at the end of this webinar session, and we will be coming back to you with another interesting webinar session soon. Thanks a lot for joining us today, and have a great rest of the week.